Hello and welcome to the course Climate Hazards and Disaster Mitigation. Today we are going to discuss bivariate flood frequency analysis using Copula. So what we learned last time, we understood the concept of compound events and their classification into preconditioned, multivariate, temporal and spatial types. We examined the physical mechanisms and interacting drivers that lead to compound flooding. We also appraised the concept of compound pluvial fluvial flooding. So for today's lecture, we are going to appraise the limitations of the univariate approaches for flood assessment and what is the importance of multivariate attributes. We'll also learn about marginal and joint probabilities and basic dependence measures. We'll develop an understanding of the copulas and how they can link different flood variables. And lastly, we'll estimate the chance of combined flood extremes for better risk management. So coming to the limitations, the basic limitations of the univariate approach is that they ignore interdependence. So that means two variables, they are correlated with each other, so that interdependence is not followed when these univariate approaches are designed. Second, many a times when we are dealing with univariate analysis, it assumes stationarity, so that is another drawback. Third is because it uses a single value from the entire hydrological data, like it uses just annual maximum peaks while neglects other information and that could lead to data underutilization. Also there are high uncertainties being observed for rare events, and sometimes because it neglects dependence, there is a risk of misdesign that is observed. So when we come to multivariate flood frequency analysis, here we are taking more than one characteristics into account, like we may take peak flow, volume and flood duration, and we can combine them to get more insights, so that the complexity is better captured. So you can see when we have already seen this is the peak discharge, integrating the entire discharge will get volume, and this is the flood duration. Now what is the need for multivariate analysis? When you consider multiple attributes, you focus on their diverging impacts, and you tend to overcome the drawback where only peak was considered while volume is not considered. So a flood having low peak and higher volume can also be damaging, so we have to consider all aspects. Similarly, a flood having lower volume and higher duration, that is again a damaging effect, so we should consider that. Next is infrastructure and reservoir management often need to withstand combined extremes and not a single variable maxima, so that is another reason. Third is your multivariate analysis support more resilient engineering designs, and thereby we can have informed policy decisions by evaluating the combined effects. Flood attributes such as peak and volume are mostly found to be correlated, so they are showing a large value of interdependency, and that is why they should be jointly addressed and not individually. And lastly, both individual distributions of flood attributes and the dependent structure may shift under changing climate conditions. So that means there is some changes in the data structure which is possible. So that means if we consider their joint variability, then it may happen like peak and volume are better dependent in certain period of time, and there is an upstream reservoir being constructed here, then your peak and volume dependency breaks. So if you are considering it separately, you may not encounter that effect. Now coming with the basics, what is random variable? So random variable, as we all know, it is something that is subjected to chance. It has a probability associated with it. A simple random variable we can think of, if you throw a die, what are the number of instances where 1 will come or 2 will come, and we can find the probability of that. When we come to hydrology, the random variable is precipitation. What is the chance that it will rain today? So that is a random variable in hydrology. So each random variable is described in terms of outcome versus probability. So if you know the probability, you can understand what is the probability distribution of that random variable. So that will help us getting information of what is unknown. Now talking about probability, there is a concept of marginal probability. So it denotes the probability of A that is occurring irrespective of what happens with another random variable B. So if this is the probability space, so what is the probability of A irrespective of B? So B is not interfering in A. So it marginal probability thus denotes probability of a single random variable without considering other outcomes of other variables. Next is joint probability. What is the probability that A and B both occur together? So a joint probability will give you a likelihood of two random variables occurring successively, occurring simultaneously. So here when we talk about joint events, they can occur in two ways. So either by OR statements or by AND statements. So OR, that is A or B. So either it influences A or B or both. So that is called union. So this particular thing will represent probability of A and B. So A union B. Next is, if we talk about AND case, that probability of both A and B occurring. So this is this region. So you will have probability of A intersection B. So these kind of probability are called your joint probability, where both variables are considered together. Now let us see, we already saw what is marginal probability, that is probability of a single variable. Joint probability can be in two terms, either it can be union or it can be intersection. There is a third probability which is called a conditional probability. Now it is a probability of a event X occurring given that Y has already occurred. So occurrence of X is linked to Y, so that is the third probability, conditional. So why we are discussing this? Just to give you a differentiation of all probabilities. In our FFA we will be only considering marginal and joint probability, but conditional is another category of probability. Next, coming to the dependence. When we talk about dependence, that means broadly it signifies that how two variables are dependent on one another. Now correlation actually is a measure of dependence which measures the strength of relationship between two variables. So how two variables are related, whether they are weakly related or strongly related, positively or negatively, that we can find it out. So here we have two variables, let us say flood peak and flood volume, and we try to plot them. So the values here will give us an idea about the dependence, that how, so if one is increasing, is other increasing, is one is decreasing, is the other decreasing, or there is no such relationship between them. So when two or more variables are involved, we call it a bivariate or multivariate analysis, and it leads to more appropriate estimates as compared to a univariate analysis. So for correlated variables, we should always go with a bivariate analysis. So bivariate analysis examines the joint behavior of two attributes. For example, if you take peak discharge and volume, or you can take volume and duration, or you can take discharge and peak discharge and duration, to estimate the probability of their combined occurrences. For example, there is a flood of 5-day duration and there is a flood of 20,000 meter cube per second magnitude. What is the probability that both will simultaneously occur? They have occurred in the past separately, but if I want to find the worst scenario on that both are simultaneously occurring, then I need to perform a bivariate analysis. So here the black one shows the joint probability space. The red and blue, these two are the marginal distributions. So the red and blue are the marginal distributions, and they togetherly form a joint distribution of the variables X and Y. So you can very clearly tell what is the probability of X and Y occurring together in a given setup. So in univariate flood frequency analysis, what we did, we had peak flow and the return period, and we just calculate what is the changes in peak flow with return period. We had volume and we had return period. What is so return period are linked to probabilities, that is P equal to 1 by T. So you can link that to probabilities, and similarly how the duration. So these variables were independently analyzed. Now when you are trying to do a joint analysis, so we want to capture what is their joint behavior. So we have volume and peak and their joint behavior. So here you can see these are all return periods. So let us say this particular point. So what is the return period? So you can see that return period is more than 100. So peak, if I want to interpret this diagram, I'll just take the point here, I'll take the value here. So that means flood volume close to 83 into 10 to the power 5 meter cube, and flood peak of 22,500 meter cube per second. They are jointly occurring, having some return period, let us say 110 years. So what is the probability? Probability is 1 upon 110. So this is how we can interpret a bivariate result. So for example, if we take this particular event, so you can see that the peak is very high. Again, peak may be close to 21,000 meter cube per second, but you can see the volume is very less. What is the volume? Volume is close to maybe 52,000. If we take another this event, what happens in this event? The volume is same, but the peak is less. So that is why if you take a univariate assessment, so we have seen 3 different events, A, B and C. If you take a univariate assessment and you go with that, you miss this complex interplay between 2 variables, that the peak may show the same return period, but there can be difference in the volume, and the volume may show the same return period, but there can be peak difference in the peak. So that is why the joint behavior has to be analyzed. For analysis of the joint behavior, there is a mathematical concept called copula. So copula is a function that joins or couples a multivariate distribution function to its one-dimensional marginal distribution function. So these are marginals, so we call them as marginals, and they are coupled together in a joint space to get the joint distribution of the 2 variables. So these are then modeled using copulas. So copula will just couple 2 things. So if you have a random vector x1, x2, xd, and the marginals are continuous CDF, that is fi equal to probability of xi less than equal to x. So these have to be a continuous function. So when you apply the probability integral transform to each component, your vector becomes capital U1 comma U2 up to UD. So D is the D dimensional, and that is your all CDFs, that is f1 x1, f2 x2 up till fd xd. So these are the marginals which are uniformly distributed in the interval 0 and 1. So this copula is defined as a joint cumulative distribution function of this random vector. So here C stands for copula. So copula U1, U2 up to UD, that is probability of capital U1 less than U1, capital U2 less than U2, and so on, capital UD less than UD. So this is how the copula is, that it will try to combine all your univariate functions. So we are discussing a bivariate copula case. There can be a trivariate copula, and higher order variation like multivariate can also be there. So you can see that a very nice contour map where the Gumbel copula is shown, that this is a joint PDF, and in the 2-phase diagram we can see how the variables x and y are related. So in probabilistic terms, if you want to define, so that is a limit 0 to 1, this D stands for D-dimensional copula. So it is a cumulative joint distribution of the D-dimensional random vector. So the concept of independence between random variables can also be represented in copulas. So what happens in copulas, if the random variables are independent, so that is a condition to satisfy the independence. So random variables are independent. The function that describes the link between the marginal distributions of the function and the joint one is the product copula. So the whatever function you take, if that describes a marginal distribution and their joint one, that is the product copula, then you can say that the random variables are independent. If that does not converge into a product copula, then they are not said to be dependent. Conversely, if some variables are associated with the product copula, they are independent. So the variables show their association with the copula, then they are independent. So here you can see some examples of Gumbel copula being fitted to different univariate marginals and deriving their joint probability distribution. So we move on to Sklar's theorem. So it states that any multivariate joint distribution can be written in terms of univariate marginal distributions and a copula which describes the dependent structure between the variables. So let capital H be the two-dimensional distribution function having marginal distributions as f and g. So there is a copula which C such that hxy is equal to C. So copula, what is it doing? It is combining two univariate. So combining f of x and g of y. So these two univariates are combined by a copula to get a distribution function h, that is a joint distribution function. So copulas are used to describe the dependence or intercorrelation between two random variables. If f and g are continuous, then you get a unique copula for that case. So copulas provide a natural way to study and measure the dependence between two random variables. Linear correlation is mostly used as a measure of dependence. So we have used mostly linear or Pearson correlation, which we called R. So however, linear correlation is not a copula based measure of dependence. It can be quite misleading and should not be taken as a canonical dependence measure. So when you are trying to model copula, we either suggest to go by Spearman's or Kendall-Stau correlation. Why? Because Pearson only measures your linear dependence and it is sensitive to only linear relationships. So if there is a non-linearity, then your Pearson correlation will not work well. Now Spearman and Kendall, they are non-parametric measures. So they convert values into ranks and then they assess the dependence structure. So they are very useful in Spearman particularly in analyzing monotonic relationships and it captures a non-linearity and is also less affected by the outliers. On the other hand, Kendall-Stau, it shows the association based on the concordant and discordant pairs. That means the probability that two variables move in the same order. So the concordancy and discordancy is defined based on that. It is also interpreted in the same manner. It is again robust to outliers and very closely related to the copula parameters. Let us discuss some types of copula. To begin with, we have Gaussian copula. So the Gaussian copula assumes that the joint distribution follows a multivariate normal distribution after transforming marginals into standard normal distributions. So this is the simplest copula. It is widely used due to its simplicity, but it has limitation that it cannot capture extreme tail dependencies. Next is T copula. It is an extension of Gaussian copula which incorporates the behavior of heavy tails to capture the extreme dependency. So it introduces a parameter called degrees of freedom that controls the tail behavior. It is more flexible than the Gaussian copula and can better model the tail dependencies particularly related to the extreme events. So you can see that if I just say this is more a uniform structure, and next you can see that it is more an elongated structure. So each copula will show different shapes, and here also you can see that the shapes are different, so that they can model diverse conditions. Next family is the Archimedean copulas. So they are a family of copulas used that use specific generating function to model dependence. So examples are Frank copula, Gumbel copula, Clayton copula. So each Archimedean copula has its own parameter that determines the strength of dependence and tail behavior. So these copulas are used when the dependence structure displays asymmetricity or nonlinear relationships. So in case of non-linearity, you can either go with the Archimedean copula. So these are the few Archimedean copulas that is very well known in hydroclimatology. Starting with the Clayton copula, it has a very strong lower tail dependence that captures joint low extremes like simultaneous draughts, etc. So for lower dependence, Clayton copula can be used. Parameter range, that is theta, should be greater than 0. Higher theta means stronger dependence. Dependence is symmetric but emphasizes lower tail, so it will show a symmetric nature. Next is Gumbel copula. It is strong upper tail dependence used for joint higher extremes like large flood peak and volume. Parameter theta is greater than equal to 1. Theta equal to 1 means independence. So it captures extreme event clustering better than the Gaussian copula. Next is the Frank copula. Frank copula has no tail preference. It handles dependence evenly across the distribution. So I'll just go back one slide to show that you can see Gumbel copula on one side, that is it has a higher tail dependence, so that is why you can see it is more skewed here. But Frank, it appears more to be uniform because it has no tail preference. So range is, it can take all real values except 0, all real numbers except 0. Positive theta includes positive dependence and negative means negative dependence. It is more suitable for moderate symmetric dependence where extremes are not the sole focus. So if you do not focus only on extremes, you can go for Frank copula as well. So these are another some list of Archimedean copulas like Ali Mikhail Haq copula, then Joey copula, and their parameter and other things. This is from standard mathematical references, so it is already shared here. Now how to estimate copula parameters? So a dependence analysis between some correlated random variables is conducted to determine whether the dependence can be deduced from the data or not. So either you can do a graphical analysis, you can do a chi plot, k plot, or you can use statistical measures like Spearman rho or Candel's tau. So the estimation of parameter theta of a copula family that best fits the data can be obtained using different parametric or semi-parametric methods. So you can use Candel's tau, Spearman's rho, or maximum likelihood methods. Once the goodness of fit is performed to select the best copula, then that is usually taken forward to represent the dependent structure of the observed variables. The bivariate joint distribution of two flood characteristics can also be obtained using a bivariate copula model. So two variables x and y, what is their joint characteristics? We can get it from a bivariate copula model. So this joint distribution function will help us calculate the joint return period. So this will be your joint return period. So what is the joint return period between two variables? We can calculate it. Now what can be the conditions? So if we have a xy plane, so in that the first condition can be variables x and y exceed their values. So that means your x is greater than equal to x and y is greater than equal to y. That can be the first case. Second case, y but not x exceeds. So y is exceeding but x is not exceeding. Third case, x and y, neither x nor y exceed. So your x is again less than x, y is less than y, and the fourth case, that is your x but not y exceed. So there can be four cases. Based on that you can see that the probabilities are shown here, and we could find what is the joint variability or joint return period of this this setup. So as discussed earlier, there can be two cases, or and. So in or case, we check that either u is greater than u or v greater than v. So there are two variables, so this indicates or, that is resembling union, and case, that shows the intersection. Or case is also called as a disjunction, and case is also called a conjunction case. So the return period of these two events are calculated using a copula function, where we calculate mu, which denotes the inter-arrival time between two successive events. So here capital T denotes the return period. So using the or case, if you want to calculate capital return period, so capital T uv equal to mu upon 1 minus c of uv. So c here is the copula. So that is the best fit copula you take into, if it can be Gumbel, it can be Frank, Clayton. So best fit copula you can take to calculate the return period parameters. And for the AND case, it is T and uv equal to mu upon 1 minus u minus v plus c uv. So that will give you the AND return period. Now it should be noted that the return period only depends on copula and it is not depending upon the marginal distributions. However, marginals are useful in deriving the parameters, but nowhere they influence the return period. They are solely decided by the copulas. So let us understand the stepwise procedure to model dependence. The first step, we'll use dependence measure like Candel's tau or Spearman rho test. Then we'll select suitable copula families based on the observed characteristics and tail behavior. So there is a guide where if your correlation is negative, then which copula to be preferred, correlation is positive, which copula is preferred, whether you are looking for tails, heavy tails or lower tails, or generic, then you select those kind of copulas. Then you estimate the copula parameters, then you derive the copula function from its generator function, and then you construct joint probability distribution using copula and the marginal distribution to compute the joint return period for both the cases. If you can compute for either or for both the cases to find the joint flood risk. What are the implications for flood risk management? Copulas model the complex dependence by capturing the joint behavior of flood peak, volume and duration when their marginal differs. So they separate individual effects from the dependent structure and provide a very clear insight about each variable's behavior. So copulas help to improve the risk estimate by accurately calculating the joint return periods and the design floods for critical infrastructure. Flexible model selection is supported through various goodness of fit tests like Akaike information criteria or log likelihood values, which help us to identify the best fit copula. And by extending multiple variables, the copulas support resilience planning and guide climate adapted robust flood management strategies. So to summarize the lecture, key takeaways: we know that flood are multidimensional events characterized by multiple correlated attributes. So making univariate analysis is insufficient for realistic flood assessments. Marginal and joint probabilities provide foundation for multivariate analysis by describing individual flood characteristics and their combined occurrences. Copula provide a very simpler framework to model the dependent structure among the flood variables and enhance the accuracy of the joint risk or joint probabilities of the floods. And lastly, bivariate and multivariate analysis help us improve the flood risk assessment efforts, which can further help in design of resilient infrastructure. Now here's an activity for you. You can list out at least 5 pairs of hydrologic variables or processes that can be jointly modeled using copulas. For example, flood peak and flood volume, they are the higher tails, so I can use a Gumbel copula. Like that, create a small list to see how you can identify this copula suitable for each kind of pairs. Here are some additional references, some literature. There are 2 books. This book by Professor Rajib Maiti on statistical methods in hydrology and hydroclimatology. It is a chapter on copula, so it is very informative, and this is an entire book on copula, so you can refer these. So thank you for your attention, and we'll meet in the next lecture to summarize the univariate and bivariate flood frequency analysis.